Start today with the Thursday salutations. Um, let's see, we've got PLC this week. Looking for Friday on that one. We've got homework number 2, and that's going to go for Wednesday. I'm hoping to have the other ones graded back to you by the end of the weekend. So remember, PLC 3 is Friday, or yeah, Friday, and then homework 2 is Wednesday. Plus the usual quiz. And lab 2, no, lab 3 will post out tomorrow. So hopefully we'll have enough to get going on the lab by tomorrow. All right, so last time we were talking about the molecular model of the ideal gas. And so since we're using the ideal gas as a system of study for our thermodynamics, even though this technically does not really fall under thermodynamics because it's discussion of what it's made of, like I've said probably like 4 or 5 times now. We had talked about the the energetics of an ideal gas, and we came up with an expression for the pressure. But I still want this a little closer. There we go. Okay. And we came up with an expression for the pressure based only off Newtonian, like mechanical considerations, right? We went through and looked at the momentum and the collisions of a gas particle with the wall and things like that. So what we had come up with was that the pressure times the volume was 2/3 of the internal energy. And since we have the ideal gas equation of state, this is equal to nRT. And we were able to start seeing how the energy is related to the temperature. Right, by what we had called Joule's law, and then thinking of the heat getting transferred. If this was a constant volume process, right, for no work done, then we have Q equal to delta E internal. And you can see that if you differentiated both sides of this to get a delta on them, you get 3/2 times NR delta T. And that gives rise to the molar specific heat. And CV delta T. And therefore, we call the molar specific heat capacity is the 3/2. Oh wait, oops, I got that wrong. That should be an R. I jumped ahead of myself there. Ahead of myself here. That would be this. So that CV is 3/2 R. Okay, that's what I meant to write. I kind of mashed it up between the heat here being NCV delta T, like that, okay? So the molar form of the heat transfer right, would be NCV at constant volume because we've got no work done. And so we come up with the constant volume heat capacity. And then at the end of class last time, I also talked about the constant pressure heat capacity, right? Right. And so we also have the constant pressure heat capacity. Which we call CT, right? Whatever's you probably see the notation here. Whatever's constant is going on the bottom of the C here, right? P is going on the bottom because it's pressure constant here. And that's going to be, it turns out to be CV plus R. Because what we came out with was 5/2 CV. No, sorry, we came out with 5/2 R. And since this is 3/2 R already, it's just adding another R on top of it. So this is a general rule for how a material will absorb heat. Or maybe a better way to say this would be what heat a material would absorb in order to affect a particular temperature change. Okay, so at constant volume, it need absorb only a certain amount of heat in order to affect temperature rise. But at constant pressure, it needs more heat to do that. Okay. Now, I'm going to introduce a dimensionless constant here, which is just the ratio of these two. The ratio of these two molar specific heats we'll call gamma. And I'm just going to define it to be Cp divided by Cv. This is not important at all until we get to using it in just a little while. I wanted to do it now while we have the impetus talking about Cp and Cv. Okay, so we've got that. And I want to go back and talk a little bit more about the internal energies. So what we've done is, oh, and the other thing I wanted to talk about, I remember we talked also about the Maxwell-Boltzmann distribution last time, and VRMS, and the average, and the most probable, and things like that. So let me just say a word about that before I get into this other thing that I was going to do here. I was talking about what's this probability and speed. So we were talking about the Maxwell-Boltzmann distribution yesterday and the probability that something has a particular speed. I got here for you. I told you that the mathematical expression for this is, I mean, it's not that bad. It's not terrible. It goes up quadratically at low speed and then drops off exponentially at high speed. I just had Desmos plot one of these for us, so I was going to show you that. Let's see, I can share my screen here. All right, so it should look kind of like this. Well, let's see. Right? If I can just zoom in on this a little bit here. This is what it looks like. And I just put in some arbitrary numbers here. You'll see you'll see here that the equation that I put in is just some number. Doesn't matter what this is here, it's just some number times an x squared times e to the minus something times x squared. And this is, the numbers are just to get the scaling a little bit interesting so you can see the features. But you see it starts off quadratic here in the low. This is plotting y versus x, but really we know that the x-axis here is v. So this is in the low speeds right here. It's quadratic. The x squared is the thing that's dominating, and the e to the minus v squared is really small. And then as v gets bigger and bigger, it turns. There's a point at which this exponent becomes more important than the quadratic, and so it tails off away like this. And this is the tailing behavior that we were talking about last time in terms of uh, objects that have higher than the most probable speeds. Okay, so just to give you a reminder, the most probable speed is the peak, right? Because this axis on the y here is really the probability of an particle having a particular speed. So if I thought of the most probable speed being about zero point 0.9, it's a touch less than zero point 0.9 here on this scale here. Looks like it's about there. So it's maybe just about 0.87 or something like that. Can't really tell. That's the most probable speed because that's the highest peak, right? That's the most probability right there. Now, look at the way the area is distributed, since it is not a symmetric situation, right? The tail out here being longer than the up here and the low part, then the average is going to be kicked over towards the tail a little bit more. So maybe the average falls. I said that the most probable is about 0.87 or something like that. Maybe the average falls a little bit past one here, just trying to eyeball the areas. It's maybe about here between 1 and 1.1. I don't know, something like that. And then the RMS speed is even further over than that. It will show up maybe around here, 1.2 or something like that, because what I showed you in class last time is that if you calculate the RMS speed, it gives more weight to the higher numbers. So it's not just only averaging, it's also putting a little bit more into the higher numbers because of the way it's calculated. So we use the RMS speed as a kind of good rule of thumb for pretty close to the average. It's not the average, but it's pretty close usually. Um, it's this tail, right, which is responsible for particles having much greater than the most probable average or RMS speed. And that's what I was talking about yesterday in terms of the escape speed of Earth, right? The molecules in the atmosphere are able to escape if they are one of these that's way out here. Okay. This is not very spectacular in terms of its scale, but if I was saying the RMS, I'm just taking a guess here. Maybe it's about 1.2. You can see that there's going to be some, if I kind of zoom in out here, let's take a look out here before this thing gets to being zero. You can see that there's going to be some that have speed, right? We're not quite at zero. I mean, so we'd even be maybe three or four times as large, 3 or 4 times as large as the RMS speed out here, right? When you zoom in on the tail. Now, the probability is not big, meaning there's maybe only a couple, but they're there, right? So that's what the Maxwell-Boltzmann distribution looks like. Whoops, let's redo that. Okay. I'm just cutting it off. It does it the same side this way, but we're not concerned about negative velocities right now. So anyway, that's what it looks like. Just thought I'd show you that for some smiles and giggles. And let's go back here. Okay. So just drawing that again. Remember, if you need to sketch this out, remember it starts off quadratic. And then out here it's tailing off, and at some point there's a turning point here, and it's going like that so that it's not a symmetric situation. Most probable is here. I'm just guessing. Let's just say average is there. And root mean square is there. I mean, obviously I don't know, but I'm just giving you the qualitative. This is how they progress. And it's this tail that's responsible for things like evaporation at room temperature or regular temperature, right? We have a lake outside, say, or we have the ocean out here. If we didn't have this tail, then we wouldn't get some of these water molecules evaporating so much, right? And it's because they evaporate that we get clouds and rain and things like that. It's really an interesting phenomenon when you start thinking about how can you apply this to things. You can even go into crazy. You can go into crazy land and think about nuclei, protons in the sun. If they didn't have, if some of them did not have an extra high velocity, then there wouldn't be fusion because they have to overcome a positive, 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 which is called Coulomb propulsion, right? Because normally they'd be trying to get away from each other, but in the sun's core, they're traveling so fast. At least these ones out here are traveling so fast they can overcome that. Have enough kinetic energy to ascend the Coulomb barrier and fuse. So it's a ubiquitous thing. This is a pretty amazing. This is a pretty amazing discovery. So we had that, and uh, and that's what I wanted to show you. So now let's go back and talk a little bit about the internal energy things. All right. So to take off from here just a little bit more, okay, to take off from that stuff I just erased. um, well, hold on. I want to look at the specific heats. Let's look at the specific heat capacities first. Okay, we came up with this expression. We're all happy about it, right? Because we're all theorists and we're going, oh, this must be true. Well, it's not 100% true. So we derived that the constant volume heat capacity of an ideal gas should be 3/2 times R. And notice that that doesn't change with temperature. There's nothing in here except constants. Okay, so it should always be this. And this is about like 8 in the bit. So let's say this is about 12 and a half joules per mole centigrade, or per Kelvin, if you like. Okay, so is this number? This is great. We came up with this. We derived it theoretically from Newtonian considerations, and we tried to put things together. And so the first thing we're going to ask is, does it agree with experiment? Because we have to. We are scientists, after all. And the answer is maybe. So why is the answer maybe? The answer is maybe because if I take a gas like helium, it does pretty well. In fact, I think I had, gosh, I thought maybe I wrote down, I looked up some of these, heat capacities, and I thought I wrote them down, but I'm not seeing them here. Well, I'll tell you what, maybe what we do here is just go over here and say ideal gas specific heat. Let's see what we come up with. Table of specific heats. Hmm. Hmm. Let's see. I'm just looking for some data here, but everybody's doing something else. There we go. This looks promising. Here we go. I like that. Let's see if we can zoom in on that, and then I will share the screen with you. Okay, so here we go. We got okay, so this is at 300 Kelvin, but you know the temperature doesn't seem to matter. Here we'll start with argon. Argon, the gas constant, Cp, Cv in kilojoules per kilogram, and kilojoules per kilogram. This is not the molar specific heats; it's the kilogram specific heats. But take a look. If I see per kilogram, yeah, this is not really what I want. But okay, how about this? We'll take a look at this value over here, the K value on the far right. The K value that they are citing is our gamma value that I just defined for you. All right. So notice that, for example, air is 1.4. I've got argon here at 1.667. Notice that I also have
carbon monoxide at 1.4, which is interesting. Helium here also has that same 1.667. Neon 1.667. So there's something interesting going on here. You're noticing argon, helium, and neon all have this same K value. Whereas gases like nitrogen 1.4, air 1.4, carbon monoxide 1.4, why are they all equal? What's going on here? So let's do this. Let's take a look at the gamma value, Cp over Cv, right? And our ideal gas so far has told us that Cp is 5/2 R and Cv is 3/2 R. Okay. So this turns out to be 5/3. And 5/3, I'm not a mathematician, but that's 1 2/3, which is basically 1.67. Okay. That K number is this gamma value that I just defined. So if you looked at some of the gases, the K value works out great. Okay. Okay. Gamma. Argon worked out really well. Helium worked out really well. Neon worked out really well. They all had that. But then I got into gases like carbon monoxide. It wasn't this. Why was it not this? Because the ratio of the two specific heats was not the same as what we have here and here. So the question is, were we on the right track? And the answer is apparently, but we're not finished, right? Because apparently this is agreeing with the experimental data. But we're not done because there's other experimental data that does not agree with this, and we didn't make any assumptions here. Did we? Well, wait a minute. What were some of the things we thought about when we did the Newtonian analysis of the ideal gas? We thought about things like elastic collisions. Oh, well, come on. That should be okay. We shouldn't have too much problem with that. We thought about the container being rigid. Okay, if I'm a gas molecule and I hit basically anything else that is a wall of a container, I'm probably gonna feel like, ooh, that's pretty rigid right there. Um, that's not a big deal, I should think. We kind of also assumed that the reflection was specular. In other words, like a billiard ball, it hit at an angle, hit the wall at a particular angle, then bounced off at that same angle. I mean, that doesn't matter. That's not material to this discussion. But there is one thing that we did assume, although we did it implicitly. And the implicit assumption we made was that we had gas particles. And you're saying, of course we assumed we had gas particles. And when I drew them, they just looked like little, right? They looked like this. Ah, but not all gas molecules look like this, do they? This is what's known as monatomic. And this is why the noble gases are so good at reproducing this particular analysis, right? This is why we really modeled them well, because they don't bond. So notice that the other gases, nitrogen, carbon monoxide, right? These gases are not just simple spheres, okay? So we might have something that's, for lack of a better word, diatomic. And it would be a linear molecule. All right. A diatomic would mean that I have basically a barbell. I have molecules on I have atoms on either side, right? And a thing connecting them. I mean, it could be a spring, could be a bar. I mean, we don't know what it is, but there's something connecting these things. And it's these things that are independent of one another. So instead of having just billiard balls going around in a gas, I've got these things banging off each other like this, hitting like this in an ideal gas. Okay, so how does that change our analysis? Well, if we were to go back and do it all again, we would have to think about the rotational aspects of something like this molecule, where this is not going to rotate. There's going to be there's no rotation in just a ball, right? And that sounds funny, but the idea here, remember, we're assuming that these are basically points. So there's no rotation. You can't exert a torque on basically a point. There's no lever arm, right? So I'm drawing these in kind of a misleading way because we're assuming as an ideal gas that these things here are also, right? These are points and they're connected by a string and it's not going to be able to rotate along its axis, right? This way. But it should be able to rotate this way like a helicopter blade, right? Or if I put my axis this way, it should also be able to go this way, like that, right? So if I had an axis going like this, it should be able to rotate around it that way. And if I put my axis this way, it should be able to rotate around it that way, right? In other words, in other words, oh, see, I knew these whiteboard markers would come in handy. In other words, as I have it here on the board, it would be going, I have this axis. So this way, right? For this axis, it's going like this. And then for this axis, it's going like this, right? Rotating that way. But there is no possibility for it rotating this way. Now, I can do this and you can see it's rotating because you can see the logos moving around. But we checked and there's no logos on the bonds here, so we can't see that. Until, of course, the companies buy up all the rights to the bonds and then name it, and then they're going to try and put stickers on them and stuff like that so you can see them as they go around. And pretty soon, the whole atomic bonding world becomes like NASCAR, and you have just stickers all over the cars and stickers all over the bonds. And oh, look, it's a carbon monoxide sponsored by Shell. Okay, great. I probably shouldn't have said that. Okay. So we have this. Now we're going to take a slightly different look at this analysis. Rather than going back to do all of it again, why don't we try to put a slightly different interpretation on what these numbers mean, the three halves. Where does the three halves come from? So let's interpret the three halves. How much space do I have here? All right, a little bit. Let's interpret the three halves. Interpretation of the three halves. With a monatomic gas, how can it have energy? Okay, we're talking about the internal energy of a monatomic ideal gas, and we're saying, okay, it has energy, right? It has kinetic energy only. So that we are talking about its motion. Now, this is a little bit strange to think about, but how can it store energy? Well, it could store kinetic energy by moving in any of the three spatial directions, right? It could be this way, or this way. And if you think back to the derivation that we did yesterday about an ideal gas particle hitting the wall and bouncing like this, right? I looked initially at the x direction. And even though in 4A, with 4A thinking, we don't separate directionality with the energies typically, right? We don't do this. But let's suppose for a minute that the dimensionality was representative of how many different ways this particle could store energy. It can have kinetic energy in any of the three spatial dimensions, right? So the three is actually a product of the three space. Okay. So the three comes about due to the ability of the particle to move in three dimensions. Now, what's really interesting is if you think about what happens if I confined the gas to a surface? What if I had a 2D gas? Then that number would be 2. And you think, well, this is just arbitrary baloney, right? Well, actually, it still works out okay. So we're on to once again a small piece of truth here. This is or truth, I don't know, maybe is the wrong word, but it's a useful way of thinking about things. So we're going to take the 3 as being due to the ability of the particles to move around, and then we're going to say, okay, the other parts of this, the 1/2 and the r, all we have to do is just multiply these ways to have energy by 1/2 r, and we'll have the CV. Right? So to get CV, we multiply, uh, let's call that number like F or something. Due to the ability of a particle to move in 3 dimensions, we'll call that the ways that it can store energy. We'll call this F, we'll call that 3 right here. So multiply F by 1/2 R. And then all you have to do is you have to count up how many ways can our gas, the components of the gas, how many different ways can these components store energy? If it's monatomic, then the answer is 3 alone, and therefore F is equal to 3. And so we do F times 1/2 R, and it would be 3/2 R, and everything would be great. Now, if we go to a diatomic molecule, now we have to count up. Okay, what's our F? And incidentally, F does have a name. And it is known as the number of degrees of freedom, which is a little bit of an overblown name, but you kind of can see, right? How is it able to be free this way? Can it move? Can it have energy like this? Can it have energy like this? Can it have energy by doing this? It's a freedom to have energy. Okay. So F we call the degrees of freedom. And it's basically how many ways can our gas constituents store energy? The gas molecules? Okay, fine. We'll go with molecules. The gas molecules. How many ways can the gas molecules store energy? That's the answer to that question is the number of degrees of freedom. Okay, so we go through. Now let's take a look at what we're going to get with the linear molecule here. So if I have a linear molecule can still move around, right? Where's my linear molecule? Here it is. Sponsored by Expo. See, I'm not kidding. This thing can still move in. It could move this way, right? It could still do this. Could it do this? Yeah, I guess so. What about doing this? Yeah, okay, that's fair. I mean, it can do all the things that where's a good little molecule? Here's no, a good little right. Our monatomic ones can still do the same thing, right? This is not a point, so it's not that good. So it should be able to move in three space exactly like a monatomic one. So we should have three, but also now I'm going to count up. What about these rotational modes? The rotational mode of it doing this, well, that's a rotational kinetic energy, right? That's still an energy. And what about this? Well, that's also a rotational kinetic energy. Ah, but remember this, no, it doesn't have it this way. We can't tell. It can't store it this way, apparently. Okay, so let's take and say, well, wait a minute. I've got the three motional ones for the diatomic molecule. Three for 3D motion plus two for rotational motion. So my total should be 5. My F should equal 5 for a diatomic molecule. All right. So let's check the gamma number, right? That means then that if I have a diatomic molecule, all right, so now I'm going to look at CV and I'm saying to get CV, I multiply F by 1/2 R. So this now becomes 5/2 R for a diatomic gas, which is now not equal to that. Okay. Therefore, the gamma factor, remember the CV now is 5. And now the CP, I have to add an extra R onto my CV in order to get CP. I erased that, but let me just remind you here that this is CV plus R. All right, so that means I'm going to have a 7 here. And now, what is my gamma factor? Gamma factor should be 7/5, which is, wait a minute, each 1/5 is 0.2. So this is 2/5 above 1. So it's 1.2 for 1, 1.2 again. So this is equal to 1.4. Oh, look at here. This is for things like carbon monoxide. If you remember our table, nitrogen, obviously that's also basically air. So for diatomic molecules, oh, look at this, 1.4. So this, now we're onto something here. Not only have we managed to show with mechanical considerations what we think is happening, we are then able to extend that and make it a very predictive thing. Now we've got something. This is a great way of thinking because it's agreeing with experiments. So we like it. All right. Okay. So what we're thinking about here is how does the molecule or the gas particle or whatever is making up this stuff, how does it have energy? Okay. Everything will move in 3 space unless confined to fewer dimensions. So normally everything is at least going to have this one, typically. Okay. And then you have to think about this for the rotational motion. Now, we thought about 2, and I told you it was only 2 because our result is 1.4, and that agrees with experiment. If I had put in 3 here because I thought, well, it's also going to rotate this way, I should be able to have energy rotationally this way, but that doesn't agree with experiment. So apparently, we are thinking about something in a way that's useful because yes, this rotates, and yes, this rotates, but no, this doesn't rotate. And so our idea of, well, these are small and they can't store energy kind of in a spinning fashion or something like that, if you think of it that way, then apparently this is reasonable to think about. Um, okay. So, what does this mean in terms of the energies then? If I think about the energy of the gas, I should be also now able to calculate the internal energy of the gas because the internal energy of the gas is N times CVT. Right? That's what the internal energy of an ideal gas is that. So, and I think, didn't we show that last time? I think we did. Well, I had the three halves, right? And in the case of the three halves, we had the three halves R from the ideal gas equation of state. So once we take the three halves R and we generalize, and we say this is what the CV is, this becomes true for ideal gases, okay? If that's true, then the internal energy also depends on the number of degrees of freedom, which makes sense because that's how energy, right? If you're thinking about how can it have energy, and I have more bins to put the energy in, well, then I'm going to have more energy. So ultimately, this turns out to be, again, the F number here, multiplying N, R, and T, right? And this degrees of freedom is telling us how many bins of energy storage there are. Now, this is for a full sample, though. This is for this is for some number of moles, right? What if I had just the single molecule or the single particle? You can go back in your notes and look at this. But for a single particle or for a single molecule, then the energy, oops, hold it. Then the internal energy of a single gas constituent would be that number of degrees of freedom times 1/2 the Boltzmann constant times T. All right. If you go back and look at the single kinetic energies that we looked at when we looked at in the very beginning, the transforming into the single kinetic energies, the 1/2 mv squareds. That's going to translate to a 1/2 times the Boltzmann constant times T. And again, all I got to do is multiply by the number of degrees of freedom, and I'll have the number or the amount of energy for a single particle or molecule or whatever it is. Okay. Okay. Great. I want to make one other point here, and that's back up at the top with this thing. Notice that the internal energy is calculated this way for the ideal gas, and that's true for any process, right? This is basically Joule's law for ideal gases, right? This is basically Joule's law. What I want to think about is how does this relate to the first law? And if you recall the first law, which you should, okay, we have this going on. And you'd say, okay, well, if I calculate the internal energy change by using NCV delta T for the internal energy change, how are we calculating the heat? Don't we calculate heat by using the molar version of MC delta T, the sensible heat equation, right? Isn't Q equal to MC delta T? And then we use the molar form of that, right? Which would be equal to NC delta T, like this. Maybe it's CV here. And isn't that exactly the same as the internal energy change? So this should be telling you something. Your right alarm bell should be going off here. The internal energy change and the heat transferred shouldn't be the same because that has restricted you to one type of process, right? That's restricted us now. So be careful. Let's see, we'll go here. Be careful thinking about the heat because I think it's so ingrained. If you've had chemistry and you've done calorimetry before, this thing is like, oh yeah, Q equals MC delta T. That's always true, right? No. No, it isn't. Because we need to figure out, okay, if I'm going to use the molar form of this, NCV delta T, well, is the process at constant volume? What if it wasn't at constant volume? Well, then that's not true. Okay, you said, wait a sec, though. You said that there was another type of C. There's this one too, right? The constant pressure one. Okay, so what if the C here was, is it NCP delta T? Is that how you calculate the heat transferred? Well, sure, if the process is at constant pressure. What if the constant pressure is not true? What if it's constant volume is not true? Well, then you can't calculate the heat this way. But you can always calculate the energy this way, no matter what the process. Now, hold on a sec. I know what you're saying. You're saying, look, that's got a CV in it. I know. Doesn't that mean it's a constant volume all the time? It seems like it should mean that. And I just went through a big argument about how that's not true here, but it turns out it is true here because you're looking at it this way, not with the CV necessarily. Look at it this way. It's a number of degrees of freedom times nRT. Or, ooh, wait. I forgot the half. Come on, people. Forgot the half. There should be 1/2 in here. Okay, sorry about that. I had it down there, and then nobody tells me that I missed it up here. I'm gonna have to rewrite that whole thing. It's too busy now. What do I pay you folks for? F times, here, I'll even write it in a different way. N 1/2 R T. There, like that. And then put the half over there. So then you can see that the molar specific heat by constant volume is going to be F times 1/2 R. Right? That would be fine. So, okay. Please make that adjustment in your notes if you just blindly followed what I did, which you should never do. You should always wonder if I'm doing things right. Now, listen, if I think of the energy as calculated this way, then we should be fine because there's no restriction that tells us, oh, it should be at constant pressure. Oh, it should be at constant volume, right? If you look at it this way, then you might fool yourself into thinking, oh, this is only valid for the constant volume process. That's not true. Okay, it's this way and it's valid for all processes. But if I think of how to calculate the heat, then I have to know, oh, are we doing a constant volume? Are we doing constant pressure? Which heat capacity am I using? That's important, right? Energy-wise, the heat capacity isn't the important thing. What's important is the number of degrees of freedom and the energy that it can store. Okay, so think more about it in this sense rather than the upper sense. All right. Let's do a quick example here to show you what I'm talking about. Let's do this. Let's take a PV process here. And let's just, whatever. Let's just go 1 to 2 here. I'm gonna go like that. It's supposed to be a straight line. It looks relatively straight. Close enough for government work. All right, so now suppose that we are going to calculate some stuff based on this process. Okay. I'm going to move this because I need some room right here. So this is the P here, and now this is going to be pressure at state 1. I've got here pressure at state 2. I've got volume here at state 1. I've got the volume here at state 2. All right. And what I'm interested in is suppose I know these pressures and volumes, right? Suppose these are all givens. All right. What I want to do is first find what's the energy change? What's delta energy for what's the internal energy change from 1 to 2? So I'll just note here the given all pressures and all volumes. So I'll just put PI, VI here, and I want to find delta E internal 1 to 2. And then I'm going to want to find Q from 1 to 2. I want to find those two quantities for this process. All right. Okay, so let's start off by assuming we've got a diatomic gas here. All right. Let's suppose I've got a diatomic gas, and I'm going to use my 5 degrees of freedom. I've got all 5 degrees of freedom. I want to talk a little bit more about what happens past the diatomic and also what happens at different temperatures. I just want to put that off until we're done with this. If I've got a diatomic gas, then my delta E internal from 1 to 2 should be equal to this thing, right? It should equal F times 1/2 nRT. All right. I don't know. Suppose we have 1 mole of it or whatever, right? It doesn't really matter. But suppose we know that. Okay. Ultimately, you'll find out it doesn't matter if we know that, but right now you're looking at it going, well, we need to know N and we need to know T. Well, okay, it's all right. Just hold on a sec. Oh, whoops, that should be delta. See, once again, folks, stop falling down on the job here. For a diatomic, my F is 5. Okay, so I'll put in 5 for the free number of degrees of freedom. We have the N and the R, whatever, but we need to calculate the delta T. Okay, well, delta T, I would be able to look at this and I could say, well, I'm going to calculate what T is up here at state 1. And I'm going to calculate what T is here at state 2, and then I'm going to subtract them. Okay, I can go through and do that. I'm going to use the ideal gas equation of state to find these. So I know that P times V should equal NR times T. So if I'm looking at, say, P1 and V1 and T1, I should be able to solve that, right? 1, 1, and 1. So T1 is P1 V1 divided by NR. It wouldn't be different if I had put in state 2 here instead. So therefore, the difference is just these two things subtracting each other. It's P2 V2 minus P1 V1, whole thing divided by NR. And you can see now why we don't really need to know the number of moles right off the bat, because all I'm going to do is stick that into there and the NRs are going to disappear anyway. Now you'd say, well, this is all fine and dandy. Could I have done that a little easier? Sure, you could have. You could have said, well, I know that the energy is nRT. By the ideal gas equation of state, the nRT is equal to the PV. So all I have to do is delta the PV. So that means this thing here, right, is equal to F times 1/2 delta of the product PV. What does that mean? It means the numerator right here. P2 V2 minus P1 V1. You have to product it and then do the difference. Okay. Okay, so no biggie. I get this thing equal here to let's go with delta E internal. 1 to 2 is then going to equal 5/2 times P2 V2 minus P1 V1. Okay, so if I know P2 and V2 and P1 and V1, which I suppose that I did, then we can find the change in internal energy, right? Okay, next thing to do is find the heat transferred. All right, delta E internal is equal to Q plus W by the first law. So if I'm going to find Q, I really want to find W first. Note, I can't use something like this. This is not a constant volume process. This is not a constant pressure process. I can't use those heat methods of calculating. This is not going to be valid because this process does not, it's not one of my special cases. So I have to rely on the first law to help me out and fall back on doing this in order to calculate what the heat transferred is. This means we need to find what the work is so that I can take these off. Yep, so we're going to find the work here as the area underneath. Q here is going to be equal to delta E internal minus W. Okay, so let's calculate the work under here. The work done. I don't know about you, maybe you're all fancy and you like a trapezoid or something, but I see a triangle sitting on top of a square or a rectangle looking thing here. So the work done, okay? Remember, this comes out of negative P dV or negative integral P dV. Since I'm going that way from 1 to 2, then the area is going to be positive, but I know that my work is going to be negative because that means when it's an expansion and V2 is greater than V1, the work is essentially energy leaving the system. So my work should be negative overall, and that means I'm going to do the first piece here, which is P2 times delta V. That's isobaric, that's no problem. And I'm going to add to that the triangle up here, which is, well, now you'd want to be careful because it's tempting to go P2 minus P1, but that's not going to give you a positive number. You need a positive area here. And if you've had 4A with me, you know what I'm talking about. When it's like a VT of a velocity time graph, you want to do the positive leg of the velocity triangle. So we're going to do P1 minus P2 here. P1 minus P2. And then that is the side leg here. And then the other leg here is the delta V again. I'm just going to erase some of this here because I'm running over. I've got delta V again here. And so the work done should be negative that. Once again, I should be able to calculate this. If I knew what all these numbers are, then I can just put these in and calculate what this number is. I just erased what I was doing, so let me rewrite that. Q here is equal to delta E internal minus W. And so you think, well, I've got a minus already in here. Isn't it taken care of? No, you still need to take that minus and put it in. Okay, the work is negative and it's subtracted, which means ultimately you're going to add it. Okay, so I'm going to be able to take this thing here and add this thing here, and I should be able to get my heat transferred. Okay, so this is going to look like Q equaling 5/2 of this. I got the indices wrong. 2 and 2 minus P1 V1 plus the triangle and the rectangle. Now, if I look closely at this, I'm going to notice something. I have the ability to simplify this just a touch. P2 times delta V. I have a P2 times delta V over here. It's negative, and it also has a 1/2 on it. So I've got 1 P2 delta V minus half P2 delta V. So that leaves me with half of P2 delta V. That means I can make this equal to negative 1/2 P1 plus P2 times delta V. Like that. Yeah, that should work. And I should just be able to add that off this side here. And could you simplify this? Yes. We have givens, so in principle, I could calculate this with numbers. Okay. But understand the process here, right? What's the process? The process is I'm using the internal energy and the number of degrees of freedom, okay, in order to calculate that. I'm using the ideal gas equation of state in order to calculate a temperature difference so that I can calculate, or a pressure volume difference, if right, in order to get this delta E. I'm then using the first law, and I'm needing to calculate the work here in order to get the heat transferred. All right. So I guess one of the main takeaways, and I know I've stressed this already 2 or 3 times, you can't fall back on this as being gospel. All right. This is not always the truth. This is good for particular situations. However, where is it? However, this is true for an ideal gas. That is how you calculate the energy. And like I've said before, if you think of it this way with the CV in it, it gets a little bit, it gets to clogging up your mind a little bit. You go, oh, that's only true for these. No, think of it that way. Okay. And you'll do yourself a favor. Okay. Now, like I said, you could pretty that up a bit and do some cancellations and some making of different algebraic things, but you got time to do that, and I don't, so you go for it. Okay. Um, all right. So with that being said, I want to go back and look at uh more complicated than diatomic molecules, and I want to look at how are these degrees of freedom coming about? What's going on? Um, what's going on is a lot. And this is part of the reason that I struggle with this class because it's just kind of like, well, where do you stop talking about what's going on? So what we've just used here is called the equal partition of energy. And this is a very powerful theorem. And it's due to Maxwell. Yes, that's the same Maxwell. Same Maxwell as Maxwell-Boltzmann's statistics and the same Maxwell as the Maxwell equation. Same Maxwell. Um, what it's saying is kind of what I just erased over there, that the amount of energy that is stored in each particular way of having energy, in each degree of freedom, is equal. In other words, you have equally partitioned out the energy. There's no preferred way of having energy. And that kind of is appealing in some sense, right? Why would some spatial direction be preferred for these things? They have no idea. Why would a particular rotation be preferred? Why would it? It wouldn't. So the equal partition is just saying that you have at thermal equilibrium, right? You have the ability to think of all of these things have equal chance of having the same energy. So that's why the energy, that's not why, that's a description of why we think of this as the energy being equally partitioned. Um, I want to just hit the diatomic molecule one more time. Okay, the diatomic molecule connected by a bond, right? It's a barbell. And so you'd say, well, okay, we counted 3 ways of having the energy, translationally, and then we counted 2 rotational methods of having energy, modes of having energy. Okay, great, no problem. It apparently agrees with experiment. It does change, though. What's interesting here is that you can lower the temperature of the diatomic molecule to the point where the rotational ways of having energy are no longer active. It's a very interesting thing, and it's a sneak peek into quantum mechanical thinking. In other words, basically what's happening here is there is an energy level for translation. And it turns out to be what's called triply degenerate because I've got the X, Y, and Z. All three of them have basically by equal partition, they have the same energies. And that's just motion, right? That's just motion. So if I draw these things out, I'd say the translational ways of having energy, right? One for the X, one for the Y, one for the Z. They're all at the same energy. And so it's equally likely, and they all have the same amount. There's no reason that one would have more than another on the average, right? Which is what we're talking about. But then, in order to excite the rotational modes, right? I'll have two rotational modes, one here and one here. I'll just call them 1 and 2. I need to have the ability to have supplied this energy. Okay. Now, if my room temperature can only supply, for example, that much energy, right? Room temperature is an energy. T is an energy, contributes to an energy. If I can only supply that much, then the rotations can't get filled. So the rotation modes are called frozen out. They're not part of the specific heat or the energy right now. But if I increase the temperature such that my room temperature has the ability to supply that much energy, now all of these are equally filled, which is kind of a funny way to think about things. But at low temperature, and people have done this experiment, they take a carbon monoxide and they lower the temperature. And indeed, they find this behavior happening. Then you raise the temperature just enough, and typically for regular diatomic molecules, it's maybe like 100 Kelvin or so. You raise the temperature enough, and all of a sudden the rotational mode starts, right? And you can see that in the specific heat as the data changes. There's even another one on top of this, and it's because this bond does not have to be a rigid bar. It could be spring-like. So there could be what are called vibrational states. And there would be two of those up here as well, for kinetic energy of them going like this, relative motion, right? And the potential energy of when they're like this versus when they're like this. So there's two extra vibrational modes up here. Now, if I raise the temperature even further, I'm going to excite those modes. And those for a diatomic molecule gas usually are going to get excited in the upper hundreds of Kelvin. So maybe 900,000 Kelvin, 1200 Kelvin. It's somewhere in there, right? So, but it's much higher. So the excitation depends on the room temperature. So that's why many of the times you'll see in thermodynamics, everything is compared to the temperature, this energy supplied by the temperature. This is thermal energy from room temperature or whatever temperature you have it at. And that is equal to the Boltzmann constant times the temperature. Right? The Boltzmann constant, if you know the Boltzmann constant, it has units of joules per Kelvin. So it's telling you how much energy there is in a degree. And that's why this is so useful. Okay, so a little bit of extra thinking there. We'll come back to that later on, probably get back to it in the quantum mechanical. I just wanted to give you a little bit of that. Suppose that I have a triatomic. Maybe it's triangular, right? If I have a triangular molecule, I got one of these. So then I have not only these three, okay? Then I'm going to have this one, and have this one, and I'm going to have this one. Wait, did I count that one already? This one, and this one. I can't. I think that's three. If it's not, then I'm old and I can't remember what I did even 5 seconds ago. Okay, it's in the plane. It's this way, and then it's this way. Okay, yeah, I'm good. All right. So then I'd say there's an extra rotational mode because the whole molecule can turn that way. So for a triatomic or a polyatomic or something like that, you probably would have one extra rotational mode here. And then your specific heat would have gone to 6 for the F degrees of freedom, and your specific heat would have become 3 times R, 6 halves, right? 6 halves times R. So your specific heat would have gone to 3R. And indeed, once again, if you look at the data, this is what we're describing it pretty well. So this mode of thinking is apparently useful. Um, okay, so there's that. I guess the last thing I want to do for today is talk about the mean free path. And this is just something to finish off the molecular viewpoint of things here, because we're thinking of the ideal gas as a set of moving bits of stuff, right? They do collide with each other. Okay, they do collide with each other. So, um, so if you think about them colliding, we can go back to the monatomic species for a minute. This is basically how far does something travel before it hits something? This is the distance between collisions. The distance between collisions is a fairly straightforward thing to think about. And it typically has the symbol of lowercase script L. You might also see it as lambda, which I don't really like that much because lambda should be saved for wavelengths. So I'm going to use L for the mean free path. So it has, for example, one collision. In the distance, well, I'm going to get this distance wrong. Let me start that over. Let me start that over. It's the path that it travels, length of path that it travels. In some time, say delta t, divided by the number of collisions that it had in that time. And so you think, well, this is kind of a complicated thing to think about. Well, but go back to the monatomic case, right? The monatomic case is going to say, well, here is a monatomic gas atom, okay? And as this thing moves around, when's it going to hit another one? Well, it's going to hit another one when their centers are one diameter apart or less, right? If it's greater, if these two things move past each other, the distance of separating between their centers is greater than a diameter. Okay, so all you have to think about is taking, for example, one of these molecules and saying, all right, I'm just going to think about what does it look like when you travel around, right? How many times did another center of a molecule lie inside this kind of volume as the thing travels around? Clearly, there was one here, right? There may have been one about here. There was one, say here. There's one here, one there, right? They're in there. So what you can say is, how long is that path? Oh, and how many collisions did I make? Therefore, if I divide those two, I'll get approximately on average, how far does it go before hitting? All right. So this comes down to a pretty straightforward number. It's the density of the gas multiplied by the cross-sectional area of a pi d squared, right? In other words, I need the two centers to be d apart, so I just imagine that as a circle, and the area, if these two are closer than that, then there's a collision, and if it's outside of that area, then there's no collision. And the greater density means the more collision it's going to have, and therefore the lower the mean free path is going to be. All right. We can also cast this into a useful form by remembering that N over V is part of an ideal gas equation of state. So if I think of PV equals nRT, or if I think of it as NKT, then N over V, the number density, right, would be the same thing as P divided by KVT. If I take this and I put it into here, notice that this thing becomes KVT on the top divided by pi d squared times P on the bottom. Yeah. And that tells you that the mean free path goes way up if I decrease the pressure. That seems to make sense, right? If I increase the temperature, these things are whipping around a lot more quickly because the kinetic energy is up, and therefore the mean free path if I increase the temperature, then I increase the mean free path because they're whipping around and they're missing each other a lot more easily, right? If I've increased the pressure, I've decreased the mean free path. And if I decrease the temperature, right, it's a little bit easier for them to hit each other. Anyways, that's what we got for today. So this is the end of our week of class, and please take a look for a lab tomorrow. Other than that, remember your PLC this week, and I will see you. I will probably see you a little bit on Friday or Saturday or Sunday, whenever you do the labs. But this week's lab will be due next Tuesday as usual. And I'll see you again for class next Tuesday also. All right. So happy day, friends. We'll see you later.